Alright, here we go. We've got a 1-bit adder that we built. We looked at the truth table, we learned about exclusive OR, we figured out about ANDs and ORs. Now we've got a 1-bit adder. We've got two 1-bit inputs A and B. We've got a 1-bit carry in. That produces a 1-bit sum output and a 1-bit carry out. Now here's a fantastically awesome thing you can do in Logisim. I'm going to come up here and... that's not what I wanted. Right click here and say add circuit. And I'm going to call this 32-bit adder. Bam, we now have a 32-bit adder. Now watch this. If I double click main, can I rename main? Analyze circuits. I guess I can't rename main. That kind of bites. I kind of wanted to rename it. Oh yeah, I can rename it. Ha! I want to rename this 1-bit adder. Because that's what it is. It's a 1-bit adder. So if I double click 1-bit adder, there I've got my 1-bit adder that we just built. If I double click 32-bit adder, that brings me in here. I haven't built anything yet. Nothing going. Watch this though. If I single click 1-bit adder and then bring the cursor over here, what is that? Well, let's hover over it and find out. It's a 1-bit adder. It's basically this circuit kind of as a function. Now watch this. Let's get me a couple of... no, I don't want these facing to the... there we go, to the east. Let's get a couple of 1-bit values. Gah, cutting and pasting. Good. Oh, come on, here we go. Right, yep. 1-bit values. Awesome. Let's get... now we do want a 1-bit value facing south. And we want an output facing west. We'll put this one here. We'll plug this in there. And finally, a carry out, which we will have facing north. We'll put that there. We'll connect this stuff up. Watch this. Bam. Okay, 1 and 0 with no carry in is 1. 1 and 1 with no carry in is 0 with a carry out of 1. This would be 1 with a carry out of 1. This is exactly the circuit that we have up here, but down here what we've done is we've like single clicked on this, we've brought this over here. We're basically making a function, sort of like a function. We're treating a circuit kind of as if it were a function, which we can then invoke down here. This is absolutely awesome, totally fantastic. Now what does this mean we can do? Well, if you consider that sort of this is A, this is B, those are two 1-bit values, this is a carryout. Watch this. Wait, no, not yet. Let me try this again. Watch this. Great. Let's grab another of these 1-bit adders. We'll put it here. So now the carryout from the first bit plunks in here to the carry in of the second bit. We'll go ahead and copy this stuff. Move this down here. We're going to plug all that stuff in there. We'll copy paste that. We'll put this down here. Let me plug that in. There we go. We've got... where'd my carryout go? Oh, I guess I shouldn't have deleted it. There we go. Good. Now watch this. So, 1 plus 0 and 0, no carryout. Now there's a carryout. The carryout becomes the carry in here. Now we've got other bits. We've got carryout. Check this out. We're basically doing... these are the first 2 bits. These are like the low bits. These are the next highest bits. So the carryout from the lowest 2 bits becomes the carry in for the next set of bits, and so on. This is called a ripple carry adder, because what's happening is the carries are sort of rippling down this big chain of 1-bit adders. Now, it turns out we actually can build a full 32-bit adder this way. It's a bit of a pain. Let's not do a 32-bit adder to start with. Let's see if we can just add two 2-bit values together. And I want to show you how to use splitters. So we're going to have these 2-bit values here. That's not 2 bits. There we go. 2-bit value. And I'll copy, paste that down here. So those are our two 2-bit inputs. So you see we've got sort of two single-bit things here. Watch this. We can come over here and we can like individually manipulate the bits. We don't have to have kind of all this stuff here. The advantage here, watch this. I'm going to get rid of this. I'm going to get rid of this. Now what I'm going to do, open up wiring. I'm going to make a splitter. What I want is 2 bits in and a 2-bit fan out. And I want this facing, I guess I want it facing east. Ah, yeah, here we go. So what this means, this is sort of weird. See how this is black, whereas over here this like 1 bit is green. The reason this is black is because it's actually more than 1 bit stuck together. So we can't sort of make it a light green or a dark green like we can, you know, up here. Here's the dark green, here's the light green to signify that it's 0 or 1. The reason being down here, if you click on it, you can actually see there's 2 bits. And so what would that look like? Would like both of them on be like a really bright green, and 1 at 0 and 1 at 1 would be, you know, I don't know, some other color, who knows? So Logisim draws those in black, but this splitter that we went ahead and plugged in, it's got the bit width coming in is 2 bits, but then the fan out is 2, so it's fanning this out, whoops, into 2 separate bits. We're going to do the same thing. Let me copy paste this down here. We'll plug this in. Maybe pull that out a little bit. And so now what we're going to do, we're adding this 2-bit value and this 2-bit value. We're going to take the 0 bits of both of these, in other words, the low bits, and we're going to go ahead and send that up here so that the lowest bits, the 0 bit, you can almost see there's 0 and 1. Those are getting sent into this first adder. Now the higher bits, we'll go ahead and, here we go, we'll plug this in here. Actually, we can just do this. Watch this. We can actually erase this. Ha-ha! Sort of adding all of that in. Now watch this. So 1, well, that's easy. 1 plus 0 is 1 when there's no carry out anywhere. 1 plus 1 is 2. Write the output here. 1, 0. And then if we make this 2 plus 1, that's 3, 1, 1. If we add another 1 in, now it's 4, 1 with the carryout, 0, 0, right? Now, we've got sort of these single bits kind of sitting out here. That's really not that cool. Watch this. We're going to make another splitter, but for this one, we're going to say the fan out's 2, the bit width, and we're going to make it face west. Now we're going to get rid of this. We're going to get rid of this. We're going to come up here to these outputs, but we're going to make it a 2-bit output that's going to be facing west. We'll plug that in here. Oh, come on. Let me grab on. There we go. Now this bit is the low bit, and then these bits are the higher bits. There we go. Yeah, there we go. 1, 0, 0. And so now if we go ahead and sort of change this stuff around, you can see the output shows up here. 1 plus 1 is 2. Totally fantastic, and we've got this extra carryout here, because if you're adding 2-bit values together and you're getting out carryouts, then that means that you've sort of like inadvertently changed the sign, or you've had an overflow or something like that. We also, if we wanted to, we could sort of add these 2-bit values together. We could make this a 3-bit output if we wanted to sort of fully represent all the outputs, because we know that it's going to be an unsigned value or something like that. Other useful things that you can do with Logisim, this right now is just an input bit. Maybe you want this actually to be a constant. You know, you always want the carry in to be 0, perhaps. So this is a carry in of always 1, but I don't want that. I want it just to always be... Oh, well, that didn't like that at all. It's got to be hexadecimal. There we go. Yeah, so now the carry in is just like pinned to 0. It's a constant value. So you don't have to worry about there being a carry in. So check this out. This is a ripple carry adder. We're using these splitters to split off the low bits. So the 0 bit here, the 0 bit here, we're sending those to one of these adders. We're taking the carry out from that, making that the carry in of the next adder, which has the high bits of the 2 values. Then we're taking the outputs of both of those adders. We're then merging them together with another splitter that we're sort of using to reverse the splitting. We've got our output here, and then we've got our carry out down the bottom. Now you can imagine a 32-bit, what's called the 32-bit ripple carry adder, would be essentially 32 of these chained together, and you'd have 2 32-bit input values, but the splitter would go a 32-bit input bits, and then would have 32 output bits, and you'd have to just wire everything together. But that would give you the ability to add 32-bit values together to produce 32-bit outputs. It's a really, really, really cool thing to be able to do. Now, I should mention that it's a ripple carry adder. In practice, you're probably not going to use a ripple carry adder. The reason being, you have to wait for the carry-outs to ripple and become the carry-ins. It can be a little bit slow. There's ways to do it that are a little bit faster. But conceptually, you're doing addition, basic arithmetic, but you're doing it in binary. Now, you're doing it in binary, furthermore, by mixing together and, or, and not gates, and exclusive or, and things like that. And as we've seen, you can build any gate out of an and, or, and a not gate. So, totally awesome. 32-bit ripple carry adder, or at least the fundamental pieces you could use to build a 32-bit ripple carry adder. Thank you.